In the world of chemistry, pretty much everything boils down to one thing: electrons, right? But how do we actually keep track of them when they're constantly moving around, being shared, or even stolen between atoms? Well, that's where this really powerful tool called the oxidation number comes in. And today, we're going to master it together. Okay, so let's just dive right in. The whole idea of one atom losing an electron while another one gains it, that's pretty simple, we get that. But what about the huge majority of chemical bonds where electrons aren't actually stolen at all, but shared? How in the world do we decide who owns them then? That's the real challenge we need to solve. You see, just thinking about reactions as a simple gain or loss of electrons is just, well, it's too limited. It works perfectly for one type of bond, but it leaves a massive chunk of chemistry completely in the dark. It was pretty clear that scientists needed a better, more flexible, more universal system. I mean, think about it like this. With ionic bonds, it's a super clean transfer. One atom completely hands an electron over to another. It's easy to see who's who. But with covalent bonds, which are frankly everywhere, atoms are sharing. And suddenly that whole idea of ownership gets really murky. We needed a tool to bring some clarity to that mess. And that tool is the oxidation number. It's this really elegant and powerful way to account for electrons in any type of compound. Doesn't matter if the electrons are being transferred or shared. So what is it, really? An oxidation number is the charge an atom would have if we just pretend for a second that every single bond was 100% ionic. Now, the key word there is hypothetical. It's not always the literal physical reality of the molecule, but as a model, oh man, it is incredibly useful. Exactly, you nailed it. This isn't some physical property you can just go out and measure. It's so much better to think of it as an accounting system, a bookkeeping system for electrons. It's a set of rules that just lets us organize and track exactly where the electron density is shifting during a reaction. Okay, so how do we use this system? Well, it all comes down to a few core rules. And seriously, forget trying to memorize a long, boring list. If you can just master these three, you'll have the essential toolkit you need to solve pretty much any oxidation number problem you'll ever see. All right, here they are. Rule number 1. Any element all by itself, totally neutral, its oxidation number is 0. Easy enough. Rule number 2. In compounds, we've got a couple of reliable players we can almost always count on. Oxygen is usually going to be a -2, and hydrogen is usually a +1. And rule number 3, this is the big one. In a neutral compound, all the individual oxidation numbers have to add up to 0. Okay, enough theory. Let's put these rules into practice, right? We're going to solve for the unknown oxidation numbers in 2 totally different compounds, and that's going to require 2 totally different strategies. So our first challenge is calcium phosphide, or C3P2. Right away, we see it's a metal bonded to a nonmetal, which is a dead giveaway that it's an ionic compound. And for simple ionic compounds like this one, there's this fantastic little shortcut we can use. It's called the reverse swap. Just think about how these simple ionic compounds are even formed. The charges of the ions kind of swap places and drop down to become the little numbers, the subscripts. So to find the original oxidation numbers, we just reverse that whole process. Check out how this works. We take the subscript 2 from the phosphorus, and we bring it up, giving calcium a +2 charge. Then we take the 3 from the calcium, bring it up, and that gives phosphorus a -3 charge. And just like that, we know the oxidation number for calcium is +2, and for phosphorus, it's -3. Simple. All right, next up, hydrazine, N2H4. Now, with 2 nonmetals bonded together, this is a covalent compound. And that means our neat little reverse swap shortcut, yeah, that's off the table. For this one, we're going to need to break out a little bit of algebra. Don't worry, it's easy. So let's organize the problem. We don't know nitrogen's oxidation number, right? So let's just call it X. And since there are 2 nitrogen atoms, their total contribution is 2X. Now, we do know hydrogen's oxidation number. It's that reliable +1. And with 4 of them, their total contribution is +4. Now we just apply our most important rule. The sum of all of this has to equal 0. So that gives us a super simple equation to solve. 2x + 4 = 0. Okay, let's subtract 4 from both sides, which gives us 2x = -4. Then just divide by 2, and we find out that x equals -2. And there's our answer. The oxidation number for each of those individual nitrogen atoms in this molecule is -2. See? The algebraic method worked perfectly. So, we've just seen 2 different problems, and we used 2 completely different tools to solve them. Mastering oxidation numbers isn't just about knowing the rules. It's about knowing which strategy to pull out of your toolkit and when to use it. So here's your guide. If you see a simple ionic compound, go for that reverse swap. It's quick, it's visual, it's efficient. For pretty much anything else, especially covalent molecules or more complex ions, the algebra method is your guaranteed path to the right answer. It's the universal tool that always works. Okay, let's recap the big stuff. Just remember, oxidation numbers are simply a bookkeeping system for electrons, nothing more. The total for any neutral compound has to be 0. Always start with the ones you know, your givens like oxygen and hydrogen, to solve for the ones you don't. And most importantly, choose your tool for the job. The quick reverse swap for simple ionic stuff and the reliable algebra method for everything else. So now you have this fundamental tool for tracking how electrons move. And believe me, this isn't just about solving some puzzle in a textbook. This skill is the key that unlocks the whole world of redox reactions. I'm talking about the very chemistry that explains how batteries power your phone, or even how your own body generates energy. You've mastered the tool, so the real question is, what are you going to unlock with it next?